All right. Yeah. So welcome everyone to our computer science department seminar. So today it's my great pleasure to introduce our speaker, Professor Karthik Sriharan from Cornell University. So Karthik is an associate professor of computer science. His research spans machine learning, stochastic optimization, online learning, reinforcement learning, and game theory. So he is the recipient of the very prestigious Sloan Fellowship as well as NSF Career Award. And what is even more amazing is his papers actually received 2 Best Paper Awards and 2 Best Student Paper Awards in CODE, the Conference on Learning Theory, which is the best conference on theoretical machine learning. So this is really, really unusual for even for the very famous researcher. So today, Karthik he's going to talk about stochastic gradient descent, which is probably one of the most widely used algorithms in machine learning. So during Karthik's talk, if you want to ask questions, you can raise your hand and I will unmute you, or you can just type in your questions in the Q&A or in the chat. So with that, please join me in welcoming Professor Karthik Sriharan to give a talk. Karthik, the floor is yours.
Thank you so much, Konkwan. Thank you so much for having me over, and it's a complete pleasure. I guess, so first I should mention that because of this remote setup, I don't get to see your faces. I just get to see like a small selection here. So I guess it's a little bit harder to connect with the audience. So feel free to interrupt me at any point. So I know kind of if you have any questions, I'll be more than happy to kind of answer them on the way. So today I'm going to be talking about stochastic gradient descent, which I am sure does not need any introduction. It's one of these algorithms that theoreticians know, that practitioners know, and nowadays even laymen know because it's so popular and works so well. Of course, so it's more, the talk is going to be kind of which is, so first of all, it's based on work with Ayush Shikari, who's my PhD student, and Satyan Kale. And Ayush, my PhD student, is kind of one of the driving force for this. And a lot of kind of even the content for the slide, like for a lot of places I have stolen from Ayush. So thank you, Ayush, if you're listening or if you will listen to the talk. So kind of the talk is going to be a little bit of 2 things. One is kind of us trying to kind of figure out the layout of kind of the stochastic gradient descent and kind of when it works. So it's a little bit of ponderance on kind of when stochastic gradient descent works, and a little bit of kind of mathematical insights that we try to gain through I guess searching in the space. Okay. All right. And again, feel free to ask questions. So just to kind of tell you as a brief introduction into what I work on theoretical machine learning, which I'm sure you kind of figured out based on the introduction. So more specifically, I look at kind of stochastic optimization and kind of how stochastic optimization in some sense is machine learning. But I also look at kind of other topics like reinforcement learning, online learning, and so on. But today I wanted to talk about stochastic gradient descent. Kind of the reason why I was interested in this is if you kind of take a caricature world of what's happening in machine learning today. Okay, let me see. Yeah, okay. So the modern approach to machine learning today is the following, right? So you collect this large training data set, or more often you download this large training data set. And once you do this, you kind of pick your favorite model. It's typically this large, highly over-parameterized, many millions of parameter deep learning model or some other model that you kind of like. And then what you do is you basically pick a simple algorithm. So here I'm going to kind of focus on stochastic gradient descent, but typically an algorithm of the form of SGD or ADAM or ADAGRAD, which are kind of light in the sense that they're fairly simple updates, and they kind of typically work with what's called smaller batch size. Okay, and somehow this seems to be a recipe that with a little bit of parameter tuning and a little bit of cranking of your GPUs seems to work pretty well overall. And clearly kind of compared to kind of when I started doing my PhD, which was in 2006 was when I started. At that time, deep learning was still in its infancy, or at least not everyone believed it was going to be like this powerful and this successful. But now you see kind of without any, I mean, it won the Turing Award, and we know that deep learning really works, right? And on a large set of topics. Sorry, on a large set of applications, not just vision, not just language, not just speech, etc. Okay. Okay, so some observations that we can make is the first thing that's kind of curious is over-parameterization helps. And if you kind of take especially like a classic 90s book in machine learning, it's a little bit counterintuitive, at least the way it's presented in these books, right? The way it's presented is you kind of have the standard curvature that you, or sorry, it's the standard learning curve that you draw that a lot of us teach in our machine learning course, which is you have your error on the y-axis, you have your model complexity on the x-axis, and the more complex the model becomes, of course, without surprise, the training error goes lower and lower and lower because we are taking more complicated models, so we can start expressing more and more predictors. And so we start getting much smaller errors. But on the other hand, after this kind of sweet spot that is shown here, I'm not able to show my pointer, so I'm just going to, so it's this point where the test curve kind of starts curving up. So once you kind of hit the sweet spot, it seems like test error starts going up. Okay, of course, this is a caricature drawing. And to some extent, the smaller models that were kind of experimented on when these books were written in the 90s, this was in fact the case. But kind of coming to current machine learning models, it seems like the larger the parameter size that I take, the better the test losses. And this is not just, I mean, this is not just the case that you're increasing your parameters. It's in fact the case that you're increasing your number of parameters to be much more than the size of your training sample. So this is the over-parameterized regime, where if I look at D as the number of parameters and N as the number of samples, D is much larger than N. Okay, and kind of these are two papers, but you literally find hundreds of papers that kind of show this, that the more complicated my model is, the more number of parameters, the more number of layers, it doesn't matter, it seems to still be true. That kind of the more complicated my model or the more complex my model, kind of not just your training error drops, which is obvious. You can see the black line here, but also your test error seems to kind of drop. Okay, and there have, of course, been a lot of works that try to kind of answer why this is the case. And we'll focus on a couple of approaches out there that try to explain kind of why this happens. Okay, the second observation that I'd like to make is that it seems like, at least without extra tuning, smaller batch size seems to help more. Okay, the smaller your batch, so this was by this really nice work by Kesker et al., where they showed that if you train using smaller batch size, you get better accuracies compared to larger batch size. Okay, so if you notice here, the smaller batch size ones kind of seem to have a higher accuracy than the larger batch size one. And of course, there has been mixed signals here from the community. There have been papers that show that even with large batch size, you can kind of get competitive edge. You can get kind of similar performances, and you might prefer large batch size because you can parallelize and use large GPUs to kind of train your network faster. And there have been papers that do that. And there has even been kind of a latest paper that claims that, that seems to claim that large batch methods kind of without too much parameter tuning can still get you fairly good test error. Okay, of course, one caveat in most of these that I've observed is that it seems like the small batch method pretty much is off the shelf. You just take kind of your simple stochastic gradient descent. There's just one single step size. You tune it carefully, you get good enough performance. But it seems like these large batch methods seem to require more tricks out of the hat to kind of get them to be competitive. It seems like at least off the shelf, if you just take these algorithms, I would still say at least up to now, small batch methods seem to work better than large batch methods. Okay, and then the third, which I think for most practitioners is an obvious point, but in theory, maybe not so much, is that multiple epochs help. Okay, the more number of epochs I run, the better my rate is. This, to some extent, you kind of expect. And of course, again, this is one of the works that I've cited here, where they kind of look at this across four different data sets and across multiple different algorithms, SGD, path SGD, which is kind of what they propose there, AdaGrad, and so on. And so the idea here is that kind of the more number of epochs I run, it seems like your test error kind of continues to decay. Okay, and not just the training error, the test error continues to decay. Okay, but on the other hand, in theory, there are, to my knowledge, pretty much not many works that show that the more number of round epochs that I do, the better kind of accuracy that I get. Okay, provably that I can get. So in a sense, so a caricature drawing of kind of what's happening in terms of explaining empirical success is that you have two things that are happening. One is you have these large over-parameterized models where the number of model parameters is pretty large and they are fairly expressive. And then the second is you have some simple algorithm like SGD. And here we're going to concentrate specifically on stochastic gradient descent. Okay, and to kind of give you a quick overview of what each of these means, over-parameterized, I mean that the number of parameters, D, is much larger than N, which is the number of samples. And SGD is just the simple algorithm, which most of you would have seen. Basically, the idea is that you are training a model where the parameters are kind of written down as a vector, W sub t, and the next iterate, the weight vector that you're going to give is going to be the current weight vector minus eta times the gradient. And the idea here is that the simple version, so there's a batch size with a capital B, which is basically number of examples you take at a time. Sorry, there's an extra eta there, which should not be. There's only a single eta in the equation. So the idea is that you basically take the average of the gradients with respect to the small batch that you take. And the question that we want to ask is kind of in terms of this batch size, how does performance vary and when does stochastic gradient descent work? Okay, so right. So the questions that we want to ask based on these observations is why does, kind of if I put it down as one question, it is why does small batch multi-epoch SGD work as well as it does? Okay, even under over parameterization. Okay, more closer look as to what I'm going to present. I'm going to first look at kind of stochastic optimization case. More closely, we'll concentrate on stochastic convex optimization case. Of course, we will go a little beyond this to kind of give some insight into what happens in the deep learning models, at least some simple deep learning models that we look at. Then we'll try to answer a few of these questions. If you haven't seen these terms, it's okay, I'll kind of explain them. First is, does the story of implicit regularization explain the success of SGD? Okay, this is this kind of theory behind why SGD works well that is quite popular today, and we'll try to see the limitations of this theory. Okay, and kind of in what sense does it work, in what sense does it not work, etc. Then we'll also see if we can show theoretical cases where stochastic gradient descent will beat what's called full batch gradient descent. That is, you set batch size equal to the sample size, the number of samples that you have. And so the idea is that on every round, you go through your entire sample and you kind of, that's on every iteration of your update. Okay, and this is kind of what used to be done back in the days when backpropagation was first introduced. And then finally, we try to figure out, of course, this is a little bit lighter than the others. We try to figure out how or when does multiple epoch training work, okay, or kind of when should you expect it to work? Okay, so I'm going to start with stochastic optimization, but before I do that, I want to make sure if there are questions, I want to kind of make sure I get them. I guess my mouse doesn't move, so I'm not sure if there are questions.
So I have a quick question. So when you say you are going to show theoretical cases where HGD beat full batch GD, so this is in terms of generalization error or what kind of risk?
So this is going to be in terms of sample complexity. So I'm going to show you
sample complexity.
So I will actually kind of discuss this more carefully when I get there, because there have been works that kind of discuss that basically show that stochastic gradient descent, in some sense, at least for convex problems, is superior to gradient descent in terms of work, which is basically, you can think of it as number of gradient computation. There has been more recent work in terms of number of iterations. Here, I'll look at sample complexity. So doesn't matter how much time, I mean, how much compute time you have, how much compute power you have, gradient descent will not be able to beat, full gradient descent will not be able to beat stochastic gradient descent. Okay.
I see.
And that's kind of what we look at.
Okay, great. Thanks.
All right. So without further ado, I'm going to just introduce a little bit of notation here. Sorry for kind of getting all the notations in one go. So I'm going to think about an instance space script Z. And the way to think about the script Z is it's basically an instance space. So kind of a classic example would be, for instance, have in mind image classification. So the space script Z consists of your instances, which are basically your image, comma, your label. So you have an image of a cat, it's labeled as a cat. So there is the image itself, there is the label cat. You have an image of a dog, and then it's labeled dog, and so on. And I'm going to look at the statistical learning framework. So there's an unknown distribution D over this instance space script Z. Okay, you can think about script D, for instance, or this capital D, for instance, as the set of all, as the distribution of all natural cat and dog images that you would kind of get in your data set. Okay, and script W is going to be the set of model parameters. So in our instance, in our case, just as an example, just think about all the weights of the neural networks that you would want to consider, or the deep learning network that you would want to consider. Okay, and then I'm going to have some notion of a loss, L, that measures how good is my neural network on the instance Z that I have. Okay, so when I look at loss here, typically think, so of course, in reality, what we are interested in is in the classification loss. But typically what's done is you take a differentiable loss, and that's used as a surrogate for the 0-1 loss that you would want. So for instance, you take something like cross entropy loss or logistic loss as a surrogate for your 0-1 loss. So you can think about this L as this differentiable loss. And what we are interested in is going to be the test loss. That is, when I draw new samples or fresh samples from this distribution D, in under expectation of these draw of fresh sample, what's my expected loss of my model parameter W when I look at its expected loss under this differentiable loss small l. Okay, and the goal in some sense is, or the goal in stochastic optimization in this case that we're going to look at, is we are given access to a training data sample, which is basically the set of images that we collected that I showed in the first slide. You have the set S that has image label pairs Z1 through Zn. So you have a bunch of dog and cat images which are labeled as dogs and cats that are drawn from this distribution. And our goal is, based on this sample S, you need to find a model parameter W hat such that its so-called excess risk is small. That is, its test error compared to the test error of the best model in this class of model parameters is smaller than some epsilon. Okay, this is going to be in a sense our goal. We want to make sure that our model is as good as the best model in some class of model script W. Okay, this is the setup that we're going to look at. And specifically for this talk, I'm going to assume two things. I'll assume a little bit more than just these two things, but definitely I'm going to assume these two things, which is that I'm going to assume that the test loss capital L is 1 Lipschitz. Again, the constant 1 is just for the talk. You don't really need it to be 1 Lipschitz. It just needs to be Lipschitz. And again, the Lipschitzness is something that you can kind of, a lot of the message that I'm going to give you will work even when it's not Lipschitz, but it has other properties. But for now, let's just think about the test loss as being Lipschitz, which means that when I look at two parameter W and W prime, or two model parameters W and W prime, their loss is upper bounded by how far away these two parameters are from with respect to each other. Okay, and I'm going to also assume that the variance of the gradients are bounded, meaning that when I look at, for the worst W in my class of models, if I look at the expected distance squared between the gradient at W of the test loss versus the, actually, sorry, there should be a gradient here. I don't have a cursor here. So there should be a gradient before the small l, that is the small loss. So we look at the gradient of the test loss versus the gradient of the instantaneous loss. Okay, and we're going to assume that this, in expectation, this norm squared is bounded. Okay, this is a typical type of a variance bound as a bound assumption that you make for stochastic gradient descent to work, and it's natural for us to make such an assumption. Again, the number need not be 1, it can be some sigma squared, and you can get bounds in terms of the sigma squared, but just for simplicity, let's make all of our constants to be 1. Okay, so this is what I'm going to assume. And now the algorithm is stochastic gradient descent. Let me kind of formally write down what the algorithm is going to be. I'm going to specifically look, at least for the initial part, for the batch size to just be 1. That is, on every, I'm going to go over my entire sample set once. So I'm going to go through these n samples exactly once, from 1 through n. And each time I update my model parameter by taking one example from my sample and moving in the direction of the negative gradient. Okay. And I'm going to return, in this case, I'm going to do an average of the iterates. That is, I'm going to return the average over these n iterates. For some of these cases, you can also do last iterate, but for now, I'm just going to do average. Okay. Okay. So now the question is, when does SGD probably work? The classic result that we know actually dates back beyond Nemrovsky-Yudin, but here I'm going to cite like the work from Nemrovsky-Yudin is that whenever the test loss capital L is convex, then SGD with the appropriate step size will work, meaning that test loss versus the best test loss is upper bounded by 1 over root n. And so as n goes to infinity, this error kind of goes down to 0. Okay, that's a classic result that if you take the Nemrovsky-Yudin book, you can find it there. Okay, and of course, this is not the only case. You can actually relax the fact that L is convex, and there have been several works here. I'm not at all doing a complete job here. There are several other works here that I should also mention, but I've just kind of given a small representation. You can have L to be convex, pseudo-convex, what's called star convex, one-point convex. It can be convex just in the path of SGD, or linearizability, which is basically kind of like convexity. You have like other kind of gradient dominance condition. These are several conditions starting from the 60s all the way up to, I guess, this current year. There have been, and again, like I'm sure in the future, there'll be more conditions under which you can show that SGD works. And pretty much a lot of, at least a majority of these works kind of rely on similar proof lines that use somehow this idea of gradient dominance. Okay. And so SGD seems to work under all of these cases. And one kind of curious fact that we will use, as you'll see later on the top, is that in all of this, I'm only talking about capital L, my test loss. I don't necessarily need to look at the instantaneous loss. For instance, I don't assume that the instantaneous loss has to be convex or star convex or any of this. You just need the test loss needs to have these properties. Okay, and it turns out that this can be pretty useful. Okay, so the first story that I want to look at is this idea of implicit regularization that's currently popular for explaining why SGD works that well. And kind of to ruin the surprise, I'm going to basically present to you a result that says that, okay, this might be true, but it cannot be true in a very broad level. So there are cases where SGD will be successful, but not for reasons of implicit regularization. Okay. Okay. So the high level idea, which definitely has to be true given the fact that SGD works, is that SGD has an implicit bias towards a good solution. There seems to be a question, but I'm sorry, I'm not. Let me just see if I can move my cursor.
Yeah, there's a question in Q&A.
Why are we differentiating between test? Oh no, capital L is the test loss. There is no, I'm not differentiating between the two. So yeah, so capital L is the test loss, and that's basically kind of the notation that I'm using. Okay, so I'll use capital L and test loss interchangeably. So we are only interested in test loss. I'm not going to specifically talk too much about training loss. We are not really interested in that. Okay. So the implicit, so as I mentioned, SGD has to have an implicit bias towards good solution. That's coming from the fact that SGD works, right? And to formally write this down, one of the ways this is formally written down is as follows. We basically say that there is an implicit regularization. More specifically, what this means is that what SGD returns, W hat SGD, is approximately either exactly or approximately going to be the minimizer of the following. It's going to be the minimizer of a regularized empirical risk minimizer. That is, you have your empirical loss or your training loss plus a regularization capital R. Okay, and kind of one of the line of works that has been pursued is that whenever SGD works, maybe there is this implicit regularizer capital R. So of course, SGD does not use this capital R explicitly. It's kind of baked into your problem. There's an implicit regularizer capital R such that SGD solution is basically this approximately or exactly the solution to an empirical risk minimizer. Sorry, to a regularized empirical risk minimizer. That is a solution that balances the regularization penalty plus the average of your training loss. Okay. Now, one thing that I want to mention here is that there is a good reason why you want to kind of consider this regularizer, implicit regularizer R to be a regularizer that is not necessarily sample dependent. Okay, so if you want to consider sample dependent regularizers, you need to be careful about how general you allow your regularizer R to be. A simple way to kind of look at this is that any algorithm, any learning algorithm can always be seen as a implicit regularized learning algorithm. When you allow R to be sample dependent, the way to look at this is if I put my regularizer to have kind of zero weight, if it exactly outputs the whatever the algorithm gives, or let's say negative infinity weight whenever it gives you exactly what the algorithm you're running would give, and zero and kind of infinity elsewhere, then basically you're completely ignoring the training loss and you're just kind of saying that my regularizer will give me a solution that will exactly match whatever my learning algorithm is going to do. Okay, so it's important. Okay, so RERM, again to remind you, RERM is regularized empirical risk minimizer. That is basically the solution to the blue equation here. That is, you have the empirical risk is basically this training loss. Training loss is also termed empirical risk. It's a terminology from statistics or statistical learning. And basically, this is a regularized empirical risk. The term that's written here because there is training loss plus regularizer. So basically, a minimizer of training loss plus regularizer is basically the empirical regularized empirical risk minimizer. So the solution to this minimization is RERM. Okay. All right. So again, at least in general, arbitrary sample-dependent regularizers would just make this problem kind of will make this problem in a sense mute, because essentially any algorithm can be written as a regularized empirical risk minimizer with respect to some sample-dependent regularizer. So we are really interested in the case where R is picked kind of in a sample-independent way. Of course, you might want to kind of consider some family of sample-dependent regularizers. Currently, our work doesn't go too much in that direction. Okay, right. So in terms of prior work that's been done around kind of regularized risk minimization and this, there has been a lot of work that basically shows that SGD solution can be looked at as an implicit regularized solution. So here is like a bunch of works that are out here. Kind of the first, say, 3 of these. So the first one shows that for matrix factorization, so the first one shows that matrix factorization has nuclear norm as its implicit regularizer when you use SGD to train it. The second one is for linear regression with either squared loss or logistic loss or log loss. And here again, you can show that it's the L2 regularization and so on. The fourth one is interesting because it's a rank rather than a norm. And these are all kind of specific instances. And you'll notice that these are all kind of, so the third one is the only one that's like deep learning, but again, it's deep learning, but with linear activation. So you need to take it with a pinch of salt. So one of the questions that I have is, what does implicit regularization mean? So what implicit regularization means is that notice that in terms of the algorithm that we are running is SGD, right? So the algorithm that we are running is this. This algorithm does not know anything about capital R. It just takes this gradient step. It just kind of runs. You just run this for n rounds or whatever. And then in the end of the day, you're going to look at your solution. So what these works claim is that there is an implicit regularization, meaning that there is some function R such that when you run this algorithm, while it's not explicitly doing it, its solution is kind of equal to the solution of this problem in blue that's shown here. Okay, so this R is called implicit regularization because we are not explicitly trying to solve this minimization problem, but the claim is that SGD is kind of magically doing it on its own. Okay, so and hence it's called implicit regularization. Okay, so there have been these bunch of works that show that there are these various implicit regularizations for various specific problems, and all of these have been basically on a case-by-case basis. And what we wanted to ask was, okay, I guess I'm missing one slide, which was the question. What we wanted to ask here basically was, is this true in general? So one of the case studies that you can take that we know already that works is that whenever we're looking at a stochastic convex optimization problem, that is where additionally we know that capital L is convex, is it true that in this case, you can explain why SGD works by showing that there is an equivalent regularizer, okay, capital R. Of course, what we are going to show is a negative result. So specifically what we show is the following. For any regularizer R that you can pick, there exists a problem for which the test loss capital L is convex. But if I look at the test loss of in expectation over samples, if I look at the test loss of my regularized empirical risk minimizer, that's going to be far away from the optimal test loss. Okay, so specifically it's lower bounded by some constant. So what this means is that because the problem is convex, in our setting, we know that SGD will work. We know that SGD will give you a 1 over root n kind of a solution that is whose suboptimality is like 1 over root n. So we know that SGD's solution is going to be 1 over root n close to being optimal. However, no regularized ERM solution can get you anything better than a constant away from the optimal solution, right? So this says that there is no way SGD's solution can be regularized empirical risk minimization. More strongly, it says that not just that SGD does not give you regularized empirical risk minimization, it's in fact true that no regularized empirical risk minimization will work for these problems. Okay. Now, I did tell you that here R is fixed before you look at the problem. In fact, this result is also true if you fix R before you, if you fix R before you look at the samples, but you can even choose the regularization parameter lambda to be something that's sample dependent. So you can basically say I do a regularization where the lambda, which is the regularization parameter, is dependent on sample, and that doesn't really make any difference. You still are going to get the same result. Okay. Now, in terms of okay, and as I mentioned before, since the problem is convex, we know that SGD will always succeed. So this kind of does two things. It says that SGD will. There are problems where SGD succeeds and no regularized ERM solution will succeed, and hence SGD cannot possibly be explained using implicit regularization, okay, at least for these problems. Okay, so in terms of the key idea that we're going to use, let me kind of spill the beans here. The key idea that we're going to use is we're going to consider problems where our test loss capital L is convex, but our instantaneous loss small l is not convex for every z. Okay, and in a sense, we're going to use this fact. Okay, because typically when you look at stochastic convex optimization, if you look at the classic definition of stochastic convex optimization, there was no notion of an instantaneous loss. There was just the notion of you're interested in minimizing the test loss and you get unbiased estimates of gradient. That's how typical stochastic convex optimization problems are defined. And then kind of at some point when stochastic convex optimization met machine learning, we kind of introduced this notion of instantaneous loss. And we automatically assume that the instantaneous loss is convex as well. But this need not necessarily be the assumption. This need not necessarily be true in many cases that we're interested in, specifically in problems like deep learning. Okay, so the key idea is we're going to look at stochastic convex optimization problems where capital L is convex, but small l is not. And specifically, the construction is going to be the following. Okay, I'm going to consider a problem where Okay, I'm going to consider a problem where it's a really high dimensional problem. I will mention briefly that later on how you can actually reduce the dimensionality of the problem. But for now, the dimensionality is going to be exponentially large in the number of samples. So it's super or parameterized. So it's not very realistic, but I can tell you that you can kind of assuage some of these issues. Okay. Now the instance space script Z consists of three things. One is a vector X and a vector alpha, which are both in 0, 1 to the D, and a label Y, which is either +1 or -1. Okay. And the instantaneous loss that we consider is the following. It's Y times the norm between W minus alpha, that is our weight vector minus this alpha parameter, Hadamard product with X. Okay. So notice that so in a sense, this is kind of saying that each coordinate of X will either switch on or switch off W minus alpha on that coordinate. Okay. And we're going to look at this L2 norm. Now, the distribution that we are going to consider is going to be the following. Okay. The distribution is that X is going to be uniform in 0, 1 to the D. So we just randomly flip coins on each of the coordinates. Y is going to be slightly biased towards being +1. So it's going to have a bias of 3/4 towards +1 and -1 with probability -1/4. It's going to be -1. And alpha is just going to be set to be a basis vector in one coordinate J star. Okay. And so alpha is deterministic in this case, in fact. And you can easily check that this loss is 1 Lipschitz because it basically looks like a norm. So it has to be Lipschitz. I'm not going to go into the details there. And the key idea is that we're going to use dimensionality, which is really large. So D here is really large, which is 2 to the n order. Okay. And you'll see very quickly why this is the case and why this is useful. Okay. So the first thing that I want to convince you here is that this, of course, this is a very toyish problem. But nonetheless, it kind of illustrates some interesting points. Okay. So the first thing is that the test loss, you can easily see that it's convex because Y is biased towards positive and it's independent of the X, right? So if I take the expected loss, that's basically what's written down here. The expectation over Y just comes out, right? And it's basically biased towards positive. So overall, it's just half expected norm of whatever is written there. Okay. And you can easily see that whatever is written in the end of this equality is convex in W because it just looks like a norm where some coordinates are switched on or switched off. Okay. And in expectation over X, in fact, if you take expectation over X, its behavior in some sense is very similar to just norm of W minus alpha. And so if you, so first of all, this should convince you that the test loss L is indeed convex and it is Lipschitz. And in this case, if the variance is going to be bounded, that's again easy to see because everything is like well and nicely behaved. And in this case, you can essentially, first of all, conclude that SGD is going to work. So you'll get a 1/√n rate for this problem. Okay.
So Karthik, can I have a question? Yeah. So if we assume the instantaneous loss is non-negative, which is also a common assumption made in the literature, would you still be able to construct such kind of negative example?
You can, I think okay, so if you just want some non-negative loss, it's not too hard to do that because essentially what you can do is just add the smallest negative quantity that you get and that'll just make the loss non-negative, right?
Oh, okay.
So that's an easy trick that you can do. Of course, in a sense, I think kind of the spirit of your question is also kind of, can you get an example that seems a little bit more realistic rather than this? I will kind of come to it. So I will kind of try to convince you that there are examples a little bit more in the deep learning world that kind of look like supervised learning, which also have these issues. There, of course, our results are not as strong, but this kind of sets the stage. The reason I'm going with this is because even though, I mean, this has lots of issues in the sense that D is super large and loss is not something that you would usually kind of consider, but nonetheless, it shows you very, like in a crystal clear way, kind of why this doesn't work, why regularization.
Okay. Sure. Thanks.
So, okay. So first of all, looking at this loss at the very end, what you can easily look at, what you can easily convince yourself is that the optimal solution, in fact, is alpha, right? Because the right-hand side, the quantity is non-negative. It's the norm of something. And when W equal to alpha, it's 0. And because X's are just random 0, 1 with equal probability, essentially the optimal solution is exactly W equal to alpha. And in fact, any solution that is even near optimal has to be really close to alpha. Okay. And so, and because of that, any solution that's near optimal should have a norm that is roughly close to 1. Okay. Now, okay. So now instead of showing you kind of the general proof that any regularizer capital R does not work, I will first just show you like a quick sketch as to why L2 regularization does not work. Once I do this, I'm going to basically like have you kind of take my word for it, or even better, you can look at the paper. Pretty much a similar line of proof will show that any regularizer, kind of the same problem instance, will not work for any regularizer. Okay, but for now, I'm just going to say that let's just consider the case where just the function capital R is just the norm squared, L2 norm squared. Okay, but again, as I will mention, it actually holds true even for arbitrary R. Okay, so we're going to start with the L2 regularization case. R of W is going to be lambda times norm of W squared. Okay, so this is the typical kind of ridge regression type of, or kind of the L2 regularization type of a scenario. And
hi, excuse me, can I ask you some question about the alpha?
Yeah, go for it.
Yeah, can you go to the previous slide about the definition of the alpha? Yeah, I'm just wondering, here alpha equal to EJ star, it means that it's alpha equal to 1 on the J star coordinate, right?
Yep, that's right.
Yeah, I just wondering, how do you choose this J star or J star?
Right. So I will show you an example for the L2 regularization. You can pretty much choose J star to be whatever you want. So I'm going to choose J star to be 1. But when you want to prove this result for a general regularizer R, this choice of J star is going to depend on R. Okay, and I'm not going to go into the detail of how it depends on R, but in a sense, kind of pick J star to be the most sensitive coordinate of the, or kind of pick J star to be the coordinate on which the regularizer is most sensitive, roughly speaking. You can look at the paper for the exact detail, but in the L2 regularization case, I'm just going to use J star equal to 1, and it works for any J star equally.
Oh, I see. So J star actually depends on the regularization you use.
And specifically, kind of one of the interesting things here is that other than J star, nothing else here depends on the regularizer. So which means that for any regularizer, it says that, in a sense, kind of the only thing that kind of depends on the regularizer is only the alpha. And again, alpha is deterministically picked. So really kind of most of all of this kind of says that even if R is picked in a crafty manner that depends on data, unless it's kind of somehow magically, unless other than this alpha part, all the other parts are kind of fixed, and you can kind of pick, so they're picked in an R independent fashion. But yes, there has to be some part that is going to be picked based on R, right? And because that's how the statement was, right? The statement basically said that there exists, for every R, there exists a distribution, and here the specific one is just the choice of alpha.
I see. Thank you. Thank you so much.
Okay, so let me kind of give you the high-level idea of why this works. So we are interested in the regularized risk minimization, which basically looks like the first equation here, right? So we are interested in a solution WRERM that minimizes our training loss, which is the first part here, plus our regularization, which is lambda times norm of W squared. Okay. And kind of the key thing here is that because the dimensionality is that large, because the dimensionality is 2 power n, with a constant probability, there is going to be a coordinate j hat. So roughly speaking, think about it as follows, right? You have basically, you have n samples, and you have 2 to the, d is roughly 2 to the n. So which means that pretty much any sequence of plus minus 1, any sequence of plus minus 1 values for y1 through yn is achieved on one of these columns with the constant probabilities, right? So if I think about the y's 1 through n on the rows, and kind of on the column all the different dimensions, with constant probability, there has to be at least one coordinate. There has to be one column that will match pretty much any sequence I want. And here specifically, the sequence that we're going to look at is the following. We are interested in whether there's a coordinate j hat such that whenever yt is positive, j hat is going to be 0. And whenever yt is negative, j hat is going to be 1. Okay. Of course, this is on the empirical sample. This says that for every t, if yt is equal to +1, xt of j hat is equal to 0, and when yt is -1, xt of j hat equal to 1. So it's switched on only when yt is negative, and it's switched off whenever yt is positive. Okay, and this happens with constant probability because d is that large. Okay, and the second observation is that nearly 1/4 of the samples yt is going to be -1 because yt is picked to be -1 with probability 1/4. Okay, and okay, why is this important? Now, basically, again, as I mentioned to your question, if I pick alpha to be E1, which I can do for L2 norm regularization, then the following is true. Okay, I'm going to basically convince you of the following. So what I'm going to convince you is that if I look at the solution is only going to be on the line that is going to be of the form of gamma times ej hat. Okay, so you really don't need to kind of, so ideally the solution that I want to minimize my test loss has to be something that's close to alpha, right? So it has to be close to E1. So if I look at just the test loss capital L, I need to pick a solution that's really close to E1. And ideally I want to pick W star to just be equal to alpha. But what I'm going to convince you is that if you are worried about minimizing regularized empirical risk with respect to L2 norm regularization, then basically you're going to just kind of pick something that's of the form of gamma times E sub j hat. So somehow kind of doing things in the direction of j hat is going to be advantageous for us. Okay. So specifically kind of, I really wish I could move my cursor here. Actually, let me just do this. You guys are able to see my screen, right?
Yeah, we can see our screen. Yeah, you probably want to zoom in a little bit. Yeah.
Let me see if I can zoom in. Yeah, there we go. Ah, perfect. Okay.
Yeah, great.
So let me just do this so I can kind of show you with the cursor. So if I look at the empirical risk, that's the first line here, right? Now the main idea is that whenever I look at indices T for which yt is -1, essentially we know that basically for these indices, I know that basically xt is on the j hat coordinate is going to be +1, is going to be 1, right? And whenever yt is +1, which is 3/4 of the coordinates, I also know that essentially xt on j hat coordinate is going to be 0, right? This was kind of what we had in the previous slide. So the key idea here is that on coordinates where yt is switched on, xt on those coordinates are 0, and on the coordinate where on the instances where yt is -1, xt on that coordinate is switched on. Okay, so this means that when I look at this instantaneous loss, whenever I have this yt being negative here, on those set of instances, I'm going to basically have this gamma times ej hat component. Okay, and whenever yt is +1, there is no gamma times ej hat component. Okay, so that's kind of the key idea here. And once I have this, now notice that if I look at this, basically 3/4 of these coordinates are going to be 3/4 of, so roughly 3/4 n times n number of instances is going to be the cardinality of this set here that I'm summing over. Okay, because roughly 3/4 of the yt's are +1, and amongst these, if I look at on the coordinate 1, half of them are going to be switched on, right? Because x's on each coordinate is +1 with probability half and 0 with probability half. So roughly 3/8 of these coordinates are going to be switched on in this last sum here. Okay, and if I look at this first sum here, essentially what happens is that roughly half of these remaining sums are going to have this E1 component because x1 is switched on, and the remaining half, it's just the negative component or just the gamma component, which is this guy. Okay, again, in the end, kind of the exact form of this equation doesn't matter. The key idea is that whenever I go with this j hat coordinate, essentially I get some extra juice, right? Because the j hat coordinate is not switched on whenever yt is +1. And only when my loss is negative, this component is switched on. So whenever I kind of try to put weight on this component, I tend to increase the amount of negativeness of my training loss. Okay. And now kind of the idea is the following. Whenever lambda is larger than 1/4, then the regularization is strong enough. And so the best thing for me to do is just to pick 0 as my solution. Okay, because your regularization component is large enough. It's larger than whatever your training loss can be. And so the best thing for me to do is just kind of go all the way to 0 on my regularization, which is lambda times gamma squared here. And whenever lambda is smaller than 1/4, at that time regularization is not strong enough. But in this case, going with EJ hat is good. So specifically, there's some gamma which is roughly greater than 1 that you would pick, and the loss will start becoming negative. But neither of this are anywhere close to alpha, which is the solution that minimizes the test loss. Okay, so basically what this shows is that irrespective of how you pick lambda, you would either prefer 0 because you're regularizing very hard and 0 is good, or you're not regularizing hard enough, and then you pick this j hat coordinate, which is this magical coordinate that happens only on your training set, but on your test set, j hat coordinate is like any other coordinate, right? But none of these are kind of good in terms of picking E1. And that's kind of the high level kind of tool sketch. Okay. All right. So as I mentioned, so the main idea is that the optimal solution for the regularized empirical risk is going to for any lambda is never going to be close to alpha. It's either going to be close to this j hat coordinate or it's going to be close to 0. And so no regularized solution is ever going to be good. Okay, and I'm not going to go through the proof, but if you look at the paper, you'll find it. The high level idea to kind of do this for any general regularizer capital R is to pick a coordinate j star on which R is most sensitive, and to basically put your alpha to be EJ star. And pretty much kind of there's a little bit of calculus that goes on, but once you kind of work all of those out, pretty much it works. And so basically what this says is that for this problem, SGD always works because it's a convex problem, but no regularized ERM will work. Okay. And so irrespective of how smartly you pick this capital R. All right. So in terms of connection to prior work, this was something that I should mention. So there's this work on which was, I guess, titled Stochastic Optimization, where basically, in fact, I should mention that pretty much both the prior works that I know of all consider stochastic convex optimization to be a setting where small l, which is the instantaneous loss, is also convex. Okay. And what this work in 2009 basically shows us is that whenever the instantaneous loss small l is also convex, then then we know that regularized ERM with respect to L2 regularization will always work. So it means that whether SGD is exactly running regularized ERM or not, regularized ERM will always work for such a setting. And so it's very important that in our setting, the small l is not convex for every z. Okay, we use the non-convexity in an important way. And more recently, kind of a work that looks at implicit regularization and stochastic optimization as case study considers this setting where again small l is convex, but they basically show that qualitatively regularized ERM solution for any regularizer is very different from SGD solution. But nonetheless, they don't provide a hard separation in the sense that there is always a regularized ERM solution that will basically match the performance of SGD. Okay. Now, as I promised you, there is a deep learning example that you can do. I'm not going to go too much into the details, but it's roughly based on similar-ish ideas. The high-level idea is we look at a 2-layer diagonal neural network. So specifically, what is the diagonal part about it? It means that when I go from x1, which is the input layer, to the next layer, each x1 gets multiplied with just one weight w1. So if I think about the first layer weights as a matrix, it's a diagonal matrix. Okay. So this is a diagonal 2-layer neural network. And we're going to consider basically, again, our input instance x is r to the d, y is between -1 and 1. And again, the model is a 2-layer ReLU network. So we have ReLU activations. It's W2 transpose ReLU of W1 Hadamard X. That's exactly this diagonal network. And the loss function, you can pick it to be either the hinge loss or the absolute loss. I'm sure other losses will also work, but let's just stick to one of these. And basically what you can show is that for such a diagonal network, while test loss, okay. So first of all, I should mention that for these diagonal networks, it's very rare that the test loss is actually going to be convex. But nonetheless, what you can show is that for a large family of distributions, the test loss is still what's called linearizable, which means that it has a condition under which you can show probably that SGD works. However, what we can show is that ERM and also L2 regularized ERM will fail for these two-layer networks. Okay, so there's a question that says, is that for some SEO problems, minimizer of RERM can always be better than SGD? So for the problem instance that I show, we explicitly show that that's not the case. Now, one thing that you need to keep in mind is that literally, okay, so there is this, so in kind of, if you think about like generally a learning problem, for any hypothesis or for any algorithm, there'll always be a problem for which that algorithm is better than all others, or almost all the time. Okay, because imagine you pick some hypothesis. Imagine your learning algorithm is just going to constantly pick some hypothesis. Okay, now I can always create a problem for which that hypothesis is exactly the answer. And so in that case, this algorithm, even though it's not really a real algorithm, is still going to be the best one. So in that sense, yes, there'll always be an SEO problem for which, for instance, minimizer of RERM can always be better than or equal to SGD. But what we show is that for any SEO problem, SGD works, right? So in some sense, all of this is in kind of in the sense that is in a sense of kind of on the entire class, what's the rate, right? So it's like the worst case rate. So what we show here is that or kind of what is shown from classical result is that for any SEO problem, SGD always works. But what we show here is that there are a subset of SEO problems for which RERM does not work. Okay. All right. So again, so as I was mentioning, two-layer diagonal neural network, while it's not convex, it has properties that it's a property that we call linearizable, but basically it's a kind of gradient dominance property that essentially guarantees that SGD works for such a problem. And what we can show is that ERM and L2 regularized ERM does not work. Okay, and you can actually kind of lift this to multiple layer diagonal networks. And here what we can show is that pretty much the same style of distributions, linearizability goes through even if it is multiple layers, no problem. But for these cases, what we can show is that for any LP regularizer that you pick, or Schatten PA, because it's a diagonal network, essentially for any LP regularizer, there is a P-layer, order P-layer network for which regularized LP regularized ERM does not work for that regularizer. Okay, so at least it rules out kind of LP or Schatten P type of regularizers for these networks. Okay, of course, it does not rule out all forms of regularizer, but the nice thing about this is that one is it's in a deep learning example, and two is that it is an example where it's of the supervised learning form. Now, I should mention that in all of this, D is roughly of the order of 2 to the n. Now, you might think that that is not really realistic, and that is definitely true. But there are two things that I can mention. One is that, first of all, using a different construction, using error correction codes, you can actually make D to be poly n, roughly, I think, actually, in fact, linear in n. And you can have these examples to still work, except that it makes these, I mean, it makes explaining why regularized ERM does not work to be much harder. This is based on prior work by Vitali et al. And the second thing I want to mention is that even when you consider the same example, if D is not, let's say, only poly n, while you may not be able to show that regularized ERM does not work, but SGD works, you can show that SGD's performance is log n better factor always better than RERM performance. Okay, so in a sense, basically what's happening in these proofs is that we are showing that regularized ERM will always do a log D factor worse, square root log D factor worse than SGD. And when D is 2 to the n, the square root log D becomes an n factor, square root n factor. But more generally, you can still get some kind of a difference between the two performances. So the dimensionality is not too big of an issue. Okay, so the second thing that I wanted to go over is why does small batch, can we show that SGD beats full batch gradient descent? So I'm going to go over these next two more quickly. So we are going to consider two algorithms. The first is just a single pass SGD algorithm. By single pass, I mean that I go from T from 1 through N, and my batch size is going to be 1. Okay, so I'll go through my entire training sample. Each sample is used exactly once. I take each sample, take the negative direction, kind of move in the negative direction of the gradient, and I kind of repeat this up until I finish all my samples. Okay, and this is typically where classical theoretical bounds for SGD is shown. And I'm going to basically compare this with full batch gradient descent. That is, we're going to run for capital T number of steps. And on each round, we are going to basically take a gradient in the negative direction of the empirical training loss. Okay, that is basically the average of the losses, or in other words, the average of the gradients across your training samples. Okay, here on every iteration, you use the entire training sample. Now, in terms of, okay, so the first thing that I should mention is that typically as T goes to infinity, a lot of times what you can show is that gradient descent starts to go close to an ERM. And so it's fairly easy to kind of construct a problem where gradient descent, if we run to convergence, meaning that you run it until it kind of converges to a solution, you can easily show that that fails. And that was already known even for earlier for lots of problems. But what is interesting here is that we show that this is going to be true even if you tune your step size and kind of allow for things like early stopping or kind of take smaller step size, run longer and so on, right? And we show that even in this case, gradient descent can never do as well as stochastic gradient descent, okay? So in terms of comparison, so there have been several comparisons. So this was one of the questions that was asked earlier. In terms of comparison between SGD and full batch gradient descent. So there has been kind of past work of two kinds. One is where you compare the work, which means that you look at the total number of gradient computations that SGD does versus that GD does. Okay, and here kind of there has been the explicit comparison was not done back in '83. I think the result was known back in '83, but kind of explicit comparison was done more in the machine learning world, where basically what is interesting is the following. You run SGD with a single gradient computation on every iteration. You go through your entire sample once. So n gradient computations, and you pretty much get the worst case optimal rate. So SGD will get you the 1/√n rate, which is pretty much the min-max rate for these problems. So SGD with a single pass over your data does optimally well. And the interesting part is that gradient descent on the full batch gradient descent will require order n gradient computations on every round, right? So this means that even if I run gradient descent for more than constant number of iterations, gradient descent is already, full batch gradient descent in terms of work is already worse than SGD. Okay. I'll come to the question when I summarize towards the end as to why I think SGD works. I don't have a very clear hypothesis, but I have some kind of hints in that direction. So the second one in terms of separation between SGD and gradient descent, full gradient descent, is a more recent work, which is kind of more in line with kind of recent developments where it's been seen that you can do kind of large batch methods with the use of parallelization and so on. So you're just interested in number of iterations that's required. And here what they show is that there is a separation between gradient descent and stochastic gradient descent in terms of number of iterations, meaning that gradient descent requires order n squared number of steps to match what SGD, single path SGD would do. So it requires a lot more number of iterations. But both of these works consider the case where, I mean, in both of these works, the examples that they consider and kind of the low bounds that's given, it's always true that gradient descent can in fact match the performance of SGD. Okay, what we are interested in is there a case where gradient descent is inferior to SGD in the sense of sample complexity? That is, if I have n samples, SGD with n samples will always do better than GD with the same n samples, irrespective of how long you run, with what batch size you run, sorry, with what step size you run. Okay, so right. So the low bound that we show is the following. It's not very appealing because it has n to the -5/12. And I mean, of course, the hope is that we can improve this, but it is the low bound that we do have. So the low bound that we have is the following. There exists a problem where the test loss L is still convex, but if I run full gradient descent, irrespective of the step size eta and irrespective of number of iterations T that capital T that I run to, gradient descent, like the performance of gradient descent is no better than n to the minus 5 over 12. On the other hand, SGD always gets an 1 over root n rate, and 1 over root n, to give you a comparison, is n to the minus 6 over 12. So SGD is slightly better than GD. Of course, I do expect that GD is going, I mean, I do expect that the lower bound for GD is not n to the minus 5 over 12, but currently kind of n to the minus 5 over 12 is what we show as a separation. Okay, so this, to my knowledge, this is the first kind of statistical separation that we know of between SGD and full gradient descent. And so, sorry. So the method is based on Amir et al.'s the 2021 paper, Stochastic Convex Optimization construction, and one more construction that we kind of combined with theirs. Okay, so what their method what their paper basically shows, they give a problem where gradient descent does work, except that it has to run for longer with smaller step size. Okay, so what they show is that larger step size for their problem is bad. So meaning that if you use larger step size, the problem is kind of, you're not going to get a good optimal solution. You'll get a worse rate than what you would, than the 1 over root n rate. Okay, but with the smaller step size, they do show that if you run for n squared number of steps, then you do get the optimal rate. Okay, what we do is we kind of append to this an additional kind of construction where we show that if I append to this kind of extra set of coordinates, and on these coordinates, what we show is that if you, on these coordinates, you will completely fail if you use small, sorry, this should not be small batch, this should be small step size method. So anytime I take smaller step size, these methods will for this example, it will completely stall. Okay, so that's the high level idea. So again, to kind of summarize, what we have is the following. We're going to look at a test at an instantaneous loss, sum of two things, L1 and L2, where L1 is their construction. And in their construction, large step size means that you get suboptimal rates. And L2 is our construction, where small step size basically means that you're not going to get a good rate at all. Okay, we basically stall in the sense that we'll stop moving at some point. I'll explain how in just a minute. And then the idea is that because you're going to kind of split your problem instance into W1 and W2 coordinates, and we can put these two together. Okay, more specifically, what we show is that if eta is worse than n to the minus 5 over 4, that is, if eta is larger than n to the minus 5 over 4, then gradient descent only yields like n to the 5 over 12 type of rate, which was a lower bound on the L1. Capital L1 is the test loss on their part, and capital L2 is the test loss on the small L2 part, that is our part. And what we show is that if you kind of consider small step size, then our method, on our problem, small L2, kind of the method fails. Okay, the high level idea for the L1 is kind of, it's roughly based on the type of constructions that I showed you earlier for the implicit regularization. I'm not going to go through the details there. I'll show you a little bit of the intuition for why L2 works. Okay. I will come back to your other question as well. Okay, so why small batch method fails, or kind of what kind of problem does it fail? First is we're going to pick a simple problem where the test loss just looks like this. It's nice convex and it's going to look like this. It's in fact going to be a one-dimensional problem. And the way we're going to kind of make this hard is the following. This is a test loss, but in terms of each sample, what happens is that we're going to randomly pick some interval which is of a really small length, which is n to the minus 5 over 4 interval. And what we're going to do is that on this interval, the following is going to happen. Okay, the test loss is just a straight line on that interval. But the way the training loss is going to be is that it's going to, or the way this is going to be is it's either going to be this red curve or it's going to be the green curve. Okay, and notice that the average of the red and the green curve is exactly the straight line. So the test loss is exactly a straight line. But then with probability half, you're going to get the green curve. With probability half, you're going to get the red curve. Okay, but notice that both in the green and the red curves, there is this flat region. And if gradient descent or if any method, gradient-based method goes to this flat region, it's going to get stuck there, right? Because the gradient there does not move, and so it just gets stuck there. And basically, the idea is the following. If I take large batch methods, with high probability, it's going to kind of skip all of these really small intervals because they are kind of randomly kind of sprayed around. And they are of really small length of n to the minus 5 or 4. But so with a high probability, a large batch method just jumps over all of these small kinks. But when I run a small batch methods, like the one shown in the green, it's going to eventually get to one of these flat regions, either the red one or the green one, depending on kind of whether we drew the green or the red on that particular region, right? So it's going to get stuck there. And in fact, this is just one instantaneous loss. You have multiple of these. So you're going to have roughly order n of such small regions. So with almost probability close to 1, you're going to get stuck, and gradient, the small batch method does not move. Okay, so this is basically the L2 construction. And kind of if you combine this with the L1 construction that I mentioned before, you'll essentially show that the result that I mentioned, that SGD works because it's an SEO problem, but for gradient descent, kind of the combination of the two, you're going to show the gradient descent can never enjoy the same kind of sample complexity. Okay, so just to quickly wrap up, the final thing that we look at is a simple variant of multiple epoch SGD, which is you run multiple epochs, but then kind of you can either think of it in two ways. Either you kind of run for capital K number of epochs and pick the best one based on some validation set, or you can kind of validate as you go and just kind of stop when you stop getting improvements. Okay, both of these kind of have similar results. So the idea here is that you're going to run for K epochs, meaning that I run SGD with kind of batch size 1 over my sample once, and then kind of I take the average over that set of samples, and then I'm going to basically kind of use that for that epoch K, and then I go one more epoch starting from that particular K as my W hat K as my starting point. Okay, this is a simple multi-epoch SGD, and what we show is that this result basically, just to kind of forget about the equation, basically what this says is that the multi-epoch SGD that I have written down here will at least perform as well as a single epoch SGD. Okay, so its test error is going to be close to the single epoch SGD plus a factor log K over M type of a factor. Okay, that's basically what this says. So this says that at the worst case, you will at least do as well as a single epoch SGD. But what's interesting is that we show that there is a stochastic convex optimization problem where for any regularizer, kind of regularized ERM does not work. And then what we show is that one pass SGD will get you a 1 over root n rate, while a K pass SGD can get you a 1 over root K n rate. Okay. So it says that if I take multiple passes, I get better and better with a factor of 1 over root number of epochs. Okay. And again, since I'm kind of running out of time, very quickly to kind of just give you what the key idea is. The idea is as follows. We basically we combine our example from the first part for implicit regularization. Actually, I'm just going to go to this slide. Okay, we are basically going to do the following. The high level idea is that each time I go to the next epoch, it's as if I'm getting fresh sample. Okay, so the idea is that there's going to be some component of this loss function that kind of says that the first epoch I run, it reveals some part of the training sample that's only revealed for the first epoch. And when I kind of reach the second epoch, I start getting kind of a different view of the same training sample. So it's as if I'm getting fresh samples. Okay, and that's why you get the rate that you get at a high level. And the exact way it's set up is kind of written down here. It's not really important. Kind of the high level idea is that epoch 1, you're kind of in the first part of the sum. Epoch 2, you'll go into the second part of the sum when you run a gradient-based algorithm. But the nice thing is under test loss, kind of, it doesn't matter because Z1 and Z2 are kind of, actually the second one should have been Z2, sorry about that. Basically Z1 and Z2 are drawn from the same distribution. So the test loss kind of does not matter whether you're kind of taking from Z1 or you're taking from Z2. Okay, the details here does not matter. The main thing is just the take home message, which is that there is a problem, or there are problems for which multiple epochs does help. It can help you up to a factor of 1 over root K, while single pass SGD kind of stops at 1 over square root n. And for these examples, things like gradient descent and full batch gradient descent and regularized ERM still don't work. Okay. All right. So I just want to summarize. To summarize kind of what we have shown is the following. The success of SGD cannot broadly be explained by implicit regularization. Now, of course, this might still be true that for when we have problems with more structure, there might be an interesting regularizer that explains the performance. I'll just finish the two summaries points and then I'll take the question. So the small batch, so the second point is that small batch size can help. And so, of course, this does not necessarily exclude all large batch methods, but what it at least says is that kind of the vanilla gradient descent, you need to be a little bit more careful, or at least there are problems where vanilla gradient descent can be inferior to vanilla stochastic gradient descent. Okay, and then multiple epochs does help. There was a question.
Hello.
Yeah.
Can you go back to the result for multiple epochs?
Sure.
So I have a question about this result. So first, I just want to confirm. So this is just for some particular problems. It's not for some general problems, right?
Yeah. So this basically says that there are problems for which this happens. It's not for general.
Yeah. And another question is that by looking at the last bullet, with using multiple epochs, the result can be arbitrarily good, right? Like the gap, the generalization gap can be arbitrarily close to 0.
Right. Right. So basically this says that as k increases, so if I do, for instance, like say poly n more epochs, then let's say I do n epochs, this says that there's a problem where if I do n epochs, I get a 1/n rate rather than a 1/√n rate. So that's what this says. I think kind of the way to look at this theorem is to kind of, you have to look at it with conjunction, which what I showed in the previous slide, which was to say that this algorithm, which returns W hat MP, is at least as good as single pass, right? So of course we are not claiming, so what we are claiming is that this algorithm is that we show is no worse than single pass. So therefore on any problem, you're never going to do worse, but it says or never worse than kind of whatever that log K factor is. But there are problems for which you can do much better.
Yeah, but my feeling is that you're only given n data. How can you like exactly to get the optimal solution of the population risk?
Sorry, what? I didn't get that part.
Because by looking at this last result, you can I can assume that you can almost achieve the global minimizer of the population risk, because this generalization gap can be arbitrarily close to 0.
Right. So, I mean, again, kind of what this says is that for any k, I can create a problem for which 1/√k, right? So it does not say that, I mean, yeah, so it's not necessarily, so you still have only n samples. It's just that each sample, in a sense, is hiding features.
Okay, got it.
Kind of, in a sense, you on every epoch, you only get to see kind of one facet of your data. So you can just, so of course, the way we kind of construct this is that we just kind of make it a large dimensional problem. And then on every epoch, you kind of just see one subset of this dimensions.
Okay.
In reality, kind of what might be happening is that it's not that you see a small fraction. What might be happening is that most of the action might be happening in a small set of directions. But then when you go to further epochs, the action might be happening in a different set of directions.
Okay.
And so in a sense, it's as if you're getting fresh samples.
Yes. So you're saying this problem instance is constructed according to the knowledge of K, right?
Yeah, yes.
Okay, yeah, that makes sense. Yeah, I was thinking about that. You are given a problem and it holds for arbitrary K.
No.
Okay, I got it.
Right. Okay, so, okay, I guess there were two questions. Okay, so the second question I'm going to answer first, which is, can we consider a tuning batch size to further improve the convergence rate? So when you say, okay, so I think, okay, so I'm going to take a guess here, because in the paper, what we do is we just kind of look at full batch versus batch size 1. But we haven't done this, we haven't gone through the details, but what I suspect is that if you go through the details of the proof, you will be able to show some kind of a mild separation in the worst case for any batch size that is poly n, like say n to the square root n and so on. We haven't done this, so I can't give you this as a full-fledged guarantee. But if you go through the proof, basically what happens is that, like, the larger I make the batch size, kind of what it says is that for gradient descent to match the performance, the step size has to be, like, if I make the batch size to be fully n, then the step size has to be really small. But it might be that when the batch size is kind of say root n, then the step size need not be 1 over root n, but it can still be smaller. It has to still be smaller than that. And then you need slightly more number of rounds, not quadratic in n, but slightly smaller number of rounds to match performance. And once you have that, you should be able to show still some separation, but you will start getting closer and closer to the 1 over root n, kind of as you decrease the batch size. I don't know kind of how this curve looks like. It's an interesting thing to look at. And the second question is there a working hypothesis? In terms of generally when SGD works, I mean, I kind of showed you a slide that showed, oh, here are several properties under which it works. Now, are those properties complete? Definitely not. I don't think so. Complete in the sense that SGD works if and only if these properties hold. But one kind of direction that that I kind of did want to kind of throw out there is the following intuition. Roughly speaking, actually, how much time do I have? 5 more minutes? Or 1 more minute, I guess. Sorry.
Yeah, you have 5 more minutes. Yeah, no worries. Yeah.
I just need a minute. Okay. So when does SGD succeed? The high level intuition is that we wouldn't really use gradient based algorithms if we expect something like gradient descent does not even work on the test loss, right? So I'm not talking about any learning. Imagine I told you what the test loss capital L was, right? Or I gave you kind of access to gradient computation. So there is no learning, there's no sample, there's just capital L, which is your test loss. Now, if you don't expect gradient descent, the vanilla gradient descent for deterministic functions to work on capital L, then to a large extent, you shouldn't really work and expect any kind of gradient based methods to work in practice. Right? That seems like of course, I'm sure there'll be like some weird counterexample to this, but I think kind of it seems like a logical statement to make that, or at least it seems like a good intuition to have that if kind of deterministic gradient based algorithm does not work for your test loss, then you really shouldn't be using kind of for learning a gradient based algorithm. Now, the second observation is that most of the theoretical examples that I showed on the slide, it turns out that kind of typically what happens is you show that gradient descent for a deterministic function capital L works or for the test loss works. And then if you're able to show success for these, you can pretty much kind of using similar proof lines up to these variance, etc. terms, and with maybe slightly different rates, you can also show that gradient descent works, stochastic gradient descent works. Okay, so if you think about the convex case, that's basically what happened. Right? You show that, oh, gradient descent for deterministic convex function works. And then you say, oh, now I'm going to get stochastic kind of estimates of gradients and kind of similar-ish proof line, you can make it work. And the same is true for things like, say, one-point convexity, alpha linearizable, all of these different examples. So one conjecture or kind of one question that we have is, assume that gradient descent on your test loss converges. Okay, so the first part has nothing to do with learning. You're given a capital L, which is your test loss, and you're given access to gradient computation of capital L. So there is no sample, there's nothing. There's just plain deterministic optimization. Assume that gradient descent on test loss works for a wide range of initialization and step sizes. Okay, I'm purposely leaving it as a vague question, but in a sense, this is kind of an interesting question that I think we should kind of look at. And under what conditions can you show that SGD succeeds? Okay, so for instance, is it true, for instance, that if gradient descent on the test loss converges whenever assume that capital L is smooth, and assume that gradient descent on the test loss converges for any initial point and kind of for a wide range of step size. So say for step sizes within the range of 1 over root n to something, 1 over n to the 3/4 or something like that, right? They succeed in terms of some kind of a rate that depends on n, then kind of can you show that it's the case that SGD will also succeed, or when is it the case that SGD will succeed? What kind of regularity conditions do you need? Because at least kind of theoretically speaking, I'm not able to come up with examples where gradient descent succeeds on the test loss, and under these kind of variance bounds and so on that you need for SGD anyways, I'm not being able to come up with examples where kind of SGD does not succeed. Okay, and these are for the classic examples. I mean, like things like convexity and all of that. Of course, you need to be careful about what you mean by gradient descent to work. If, for instance, if you consider gradient descent exactly from one start initial point, then the state question is going to be answered in the negative. But kind of the high level idea is if you assume gradient descent kind of robustly succeeds, then can you show that SGD also succeeds? Okay. And so that's kind of, in a sense, a conjecture which says that I expect the test loss to be nice enough that gradient descent works. And for these cases, I claim that SGD should also work, okay, at a high level. But again, like now, of course, you can ask the question, when does gradient descent succeed on a given deterministic loss? That, I mean, there are conditions under which, sufficient conditions under which you can show it succeeds. Necessary sufficient conditions, I don't know. I mean, like, I think kind of, that's a question that I'll come to after I kind of get, in a sense, an answer to this question. I don't know if that was exactly the answer that you wanted for your question, but that's the answer I do have for the question that was posed on Q&A. Thank you.
Yeah, thank you. Thank you for the great talk. Yeah, so maybe let's take a few more questions if the audience have questions. So I have a clarifying question, because at the beginning of this talk, you mentioned that this result is for potentially over-parameterized setting where the dimension D can be much larger than the sample size N. So I wonder, because when you assume the variance of the stochastic gradient noise, you assume it's bounded by 1 or bounded by some constant. But in that assumption, actually, in some problem settings, the variance of the stochastic gradient can depend on the dimension, right? So is there any, do you have any comment on that?
Right, okay, so I guess like a few things there, right? I think kind of there are, okay, so basically one thing that's true here, okay, so you're right in that for a lot of deep learning examples, the variance does increase with, I mean, the worst case variance can increase with the number of dimensions. But it's also true that, I mean, here I take a caricature example, right? Like I kind of assume that the loss is Lipschitz and so on. Typically, kind of, you might want to kind of consider things where you have smoothness as well. And it's also not, here we kind of were working in this nice setting where any initialization kind of within like a unit ball or something like that works. In practice, you also, your initialization also is kind of, in a sense, important. So somehow kind of in practice, what happens is for any initialization, it seems like there's something that's maybe not too far off from your initialization that seems to work. At least there are some results in deep learning that kind of suggest that the bound of kind of how far a good solution is from initialization is not too bad. And if on top of this you have smoothness, so right now kind of the way we are looking at it is you have this Lipschitzness at every point, and so effectively you're just saying that the gradient is bounded by 1, right? But if you did have smoothness, you also know that while worst case gradients might be bad, which is kind of what Lipschitz constant is, it's still true that when I run gradient descent or stochastic gradient descent, I kind of quickly start, when the gradient is really large, then I'm kind of very quickly decrease my suboptimality, right? Because in a sense, my suboptimality is roughly proportional to eta times gradient squared. So the high level idea is that if the gradient is large, then I very quickly kind of go towards kind of a good solution, or at least minimize, I kind of very quickly decrease my loss for that step. And then you're in a place where gradient starts becoming smaller. So really what really matters for SGD proof, in a sense, is the gradients or the expected gradients or the gradient of the test loss along the path of the SGD, not kind of the worst case gradient. And kind of the high level idea is that kind of if I have it with smoothness, it might still make sense in the sense sense that if the gradient is large, then I kind of quickly go to a better loss place. And then if the gradient is small, then I'm anyway in a good place in terms of kind of the gradient norms being not too bad, right? So that could be an explanation. Again, I don't know if that is necessarily the explanation. At least it's an explanation that fits.
Yeah, that makes sense. And another question is in the second part and the last part of your result about the batch size as well as the multiple epochs. You have some lower bound result. I wonder in the proof of those lower bound results, do you still need, for example, the problem dimension D is something like a 2 to the power of sample size n, or
so okay, so for the multiple epoch one, Really, the only reason why so first of all, the fact that multiple epoch works better than a single epoch, you can actually very easily kind of have that happen even for deterministic gradient descent, right? For a deterministic function. So in a sense, the result is only interesting if you're able to show that all other things fail, in the sense that RERM fails and gradient descent fails and so on. So in that sense, it combines kind of like the previous functions, constructions, along with this extra thing. So in that sense, kind of if you can improve the earlier construction, for instance, in part 1, then you can improve the part 3 as well.
Okay, I see.
Part 2, currently, I don't know if you can make D to be like order n. Currently, their proof for the F1 part, the L1 part that we take from the Amir et al. Paper, they use basically this, they use a construction similar to what I showed, which is the 2 power n. And there it's not clear whether the Vitali et al. Construction that's based on error codes kind of can reduce the dimensionality there to order like linear in n. At least, it seems like it gets way more hairier to kind of figure out what happens for gradient descent under the Vitali construction.
Okay, I see.
Part 2 alone, like for the mini batch versus full batch versus batch size equal to 1, I don't know that whether D can be made smaller. My guess is it can, except that I think it's going to be a hairy problem in the sense of keeping track of what gradient descent does in these error correction code examples is going to be pretty nasty.
Okay, I see. Okay, thank you. Yeah, that makes sense. Yeah, so in other words, all the results currently, the proof of all the results need to be done in the D is much greater than N.
Right. So I think from D being 2 to the N, you can come down to D being like order N. But I think the interesting thing, which is where the over-parameterization in a sense kicks in, is that when D is like kind of constant-ish or something like that, or when D is smaller than N, much smaller than N, then I think basically a square root over N is always possible. So in the sense that ERM will work at a rate of square root D over N. So for at least these problems. So which means that if D is like small o of N, then there is some rate at which ERM will work. So in that sense, you do need over parameterization. Now, how badly it basically says that in the under parameterized regime, these results don't hold. They actually they're not just that this construction does not hold, the result itself does. ERM will always work in those cases. And so you really do need this over parameterization to kind of start seeing these differences between SGD and kind of large batch methods or these ERM type of approaches. And I think that's probably why kind of we are seeing it now rather than, I don't know, like 20 years ago or 10, 15 years ago.
I see. Yeah. Thank you. So are there any other questions? Oh, there's a question from the audience. Yeah, if you can go ahead. Yeah, I cannot hear your voice. Hello? We cannot hear you. Okay, so maybe there's some like technical issues there. Oh, okay, that's fine. Okay, so maybe in the interest of time, we will wrap up the seminar here. So let's thank our speaker, Professor Karthik Sriharan again for the great talk. Thank you, Karthik.
Thank you.
And I will stop recording.